Welcome back, everyone. In the last lecture, we have seen inverse and inverse of matrices and inverse of linear transformation. In this lecture, we are going to see what is a determinant and adjoint. Okay. So, what is a determinant? We will see both its visual interpretation as well as some properties of determinant. So basically, the determinant is the factor by which a linear transform or a matrix, these are the same thing, changes any area. Okay, any area is called the determinant of that linear transform or matrix. Okay, so if you have seen the previous lecture in which I have seen you the visual interpretation of a matrix or linear transform, it kind of transform the input vector space. So when you are transforming the input vector space, then the area in the input vector space will also be transformed, right? So for example, there is an area composed by two vectors. So for example, this is the input vector space, all right? And you have, let us suppose, one vector here which is vector v, and let us suppose you have another vector here which is vector w, right? So the linear transform T will transform these two vectors v and w. Okay, maybe after the transformation these two vectors uh, maybe we came somewhere here, and maybe w, this is nothing but T of w, and this is T of V, right? So if you see what is the area formed by these two vectors, so you just take this vector W and place its tail at the tip of V, and you will get something like this, right? Something like this. Now the area formed by these two vectors is nothing but the area of this this is the area, right? So after the transformation, uh, uh, the area formed by the transformed vectors, right? The area formed by the transformed vectors is this, right? Is this. So the factor, the factor by which the area got changed by the linear transformation, by the linear transformation T is determinant. Okay, so for let us suppose initially the area was A1, let us suppose just A, and after the transformation the area, initially the area is, let us suppose, A. After the transformation the area is T of A. Then the factor by which the area changes, that is the factor T of A by A. This is nothing but determinant. This is determinant. Okay, so let us suppose initially the area is A unit, and after that the area is 1.5 A. So the determinant here is 1.5 A by A, that is 1.5. That is, this transformation T changes all the areas by a factor of 1.5 times. All right. So this is what a determinant do. This is what determinant mean. That is the factor by which your linear transformation or its representative matrix is changing the area of the input vector space is determinant. Now we will see a visual interpretation of it. So for example, we have this we have this matrix 3012. So 30 basically means this input in the input vector space we have I hat and j hat as the basis vector, right? So this transformation is taking the I hat vector at 3 comma 0, that is here, and the j hat vector j hat input basis vector at 1 comma 2, and this is the vector which we are of interest, 1 comma 1, right? This 1 comma 1. Now this transformation is transforming this vector 1 comma 1 to 4 comma 2. We will see this. But we will also see how the area is getting changed. So for example, this is the area. This is the area formed by the two basis vector I hat and j hat, right? So this is I hat, this is j hat. You close this thing and you get the area formed by I hat and j hat. Now we will see that after applying this matrix, I hat is moved to 3 0 and j hat is moved to 1 2, and we will see how by what factor the area is getting changed. Okay, so I will just start my visualization. So see, slowly this I hat will land here, this j hat will land here, and this vector 1 comma 1 will land at 4 comma 2, and this area will change. See, it started increasing. See, it increased further. This area, this yellow shaded region. If you see, it keep on increasing. See, and slowly we this I hat is landing here and j hat is landing here. Okay, now at the end, see, the I hat has landed at 3 comma 0, that is this column. The j hat has landed at 1 comma 2, that is this column. If you see in the background, we have that gray grid lines, right? So that gray grid lines represent the input vector space, and these blue grid lines in the foreground is the transformed vector space. What happened to the input vector space after applying this matrix is these blue grid lines. So we see that the spacing between the grid lines has increased drastically after applying the transformation. Okay, so we have seen this area as also, right? This area has been changed, right? This area has been changed. So basically, this is the factor by which this area is changed is determinant. Okay, now visually we can find this factor here itself. So for example, initially we have this small box, right? This is this unit box. This is let us suppose of unit length. So its area is 1, right? Because this is 1, this is 1. So 1 into 1, this area of the square is 1. Now after the transformation, if you see that single box has been expanded to this bigger box. Now we can see that this bigger box is composed of some smaller smaller original boxes of size of area 1 unit, right? So this is the one box. If you see my cursor, let us suppose let's pick this one. This is the first unit area box. This is the second, this is third, this is fourth. So surely we have four boxes. Similarly, if you see this one and this smaller triangle, this small triangle and this remaining portion is creating one box, right? So this is the fifth one. Similarly, this box and this smaller triangle portion is creating another box. So this is the sixth box. So if you see in the transformed vector space, in the transformed xy plane, one one such box is composed of six those smaller boxes of the input vector space. So we can clearly see that the amount by which that unit area, this the amount by which this unit area has been changed is by a factor of 6, because this transformed area found by the transformed I hat and transformed j hat is composing those six smaller unit squares, right? For 1, 2, 3, 4, these two are the fifth one and these two are the sixth one, right? So the factor by which this matrix or this linear transformation is changing the area formed by the unit basis vector I hat and j hat is 6 times, and this is for any area. You just not take the this square area. No need to take this square area. If you take any area, so basically, if I simply create one more area here, some zigzag area, then the factor by which this area has been changed, that is 1.5, by the same factor this area will also be changed, so this will become little bigger. that is 1.5 times. Okay, so this is true for any area in the input vector space. All the areas in the input vector space are got changed by the same factor. Always remember this. Okay, irrespective of the shape. Okay, so and we can also see the determinant. So how we calculate the determinant? We multiply these two, 3 into 2, 6 minus 1 into 0, 0. So 6 minus 0, 6. So we can see that the determinant is 6. And we have seen visually here also the factor by which the area is increased is 6 times. So this is what determinant is. Okay. So I think you get the visual interpretation of determinant. Okay, now we will see an interesting linear transformation or matrix. So let us suppose in the previous lecture we have seen this matrix, right? 1 0 1 0, right? 1 0 1 0. So if I simply move this to 1 0, this is not nearly 1 0. Okay, so this is almost nearly 1 0 1 0. So if I say this, then after let's see its transformation. You see that in the previous lecture we have seen that this matrix, because this matrix, the rank of this matrix is 1, the both the columns are linearly dependent, they are exactly same. So this matrix inverse doesn't exist, and this matrix is from R2 to R1, right? This takes the vectors, this matrix A is from R2 to R1, right? This takes vector from 2 dimension to 1 dimension, right? And we are seeing it here. Slowly, this input vector space, which is the R2 space, is getting squashed onto a line, that is the x-axis. See, this blue region is the input vector space, and it is slowly getting squashed onto the line. So now tell me one thing. If this input vector space is squashed into a line, then any area which is in the input vector space, let us suppose this area, right? This will also squash to onto that line. Okay, see, it is getting mapped to that line or squashed to that line. So what is the area of that region after applying this matrix or linear transformation? Zero, because there is nothing called area on a line. A line doesn't have area, right? Line is 1 dimension, but area is 2 dimensionals, right? So this matrix basically, any area in the input vector space will be squashed down to 0 in the output vector space after applying this matrix, right? And we can also see it from the determinant. What is the determinant of this? Determinant is nothing but 1 into 0 minus 1 into 0, that is 0, right? So 0 basically means the factor by which the area got changed is 0. That is, whatever be the initial area, now after applying the transformation of the matrix, the area is 0. So whenever you have a matrix which moves which transform the input vector space from a higher dimension to a lower dimension, then the determinant is always 0. Okay, so if you have a matrix A which takes the vectors from Rn to Rm, given that m is less than n, then in this case, this simply says that determinant of A is 0. Determinant of A is 0. Because see, you are wrapping this space, you are squashing the input vector space to a lower dimension. So whatever area, volume, or whatever is there in the original vector space, it will be squashed. And also see, this area is for the 2 dimension. Basically, if your input vector space is 2D, But if your input vector space is 3D, then it's volume. And if it's 4D, then it's like four-dimensional volume or five-dimensional volume. Okay. So similarly, if for example you have the input vector space, a 3D input vector space, right? R cube. So you will have a volume here, right? You will have a volume here. So if your linear transformation transform from R3 to R3, then then the amount by which this volume change, maybe this volume changed like this. Okay, the amount by which this volume changes determinant. And if you have another linear transformation T2, which is transforming this input vector space from R3 to R2, from R3 to R2, then this volume will be no more present in R2 vector space, because see, in two dimension there is no concept of volume. There is only concept of area. So there is no concept of volume. So obviously the volume is transformed by a factor of zero. Basically, whatever volume is there in the input vector space, it is zero in the output vector space, because output vector space has been boiled down to output vector space has been boiled down to XY plane, right? So whenever your matrix is transforming the input vector space from a higher dimension to a lower dimension, then the determinant of that matrix or that linear transformation is always zero. So this is an important thing to note down. Okay, there is one more thing, one more visual thing which you can note down is whenever the orientation of space is oriented by the matrix, then the determinant of that matrix is negative. So let us suppose uh, this is the input vector space. Okay, this is the input vector space, and this is your basis vector I hat and j hat. Okay. Now let us suppose you have a linear transformation T. Okay. And this linear transformation, what it does is, after applying this linear transformation, your I hat, the transformed I hat, that is T of I hat, is here, but your T of j hat is here. So you see that it got flipped, right? Initially, j hat in the input vector space, j hat was to the left of I hat if you go anti-clockwise. But in the transformed vector space, t of j hat is to the right of t of I hat. So the orientation of the basis vectors got switched. So whenever this happens, then in this case, the determinant of t, the linear transformation t or its matrix, is negative. It is going to, obviously it will have some magnitude 2 3 0.1, any float value, but the sign will be negative. Always remember that, because its direction got orientation got changed. Okay, so for example, if you see here, uh, in this scenario, initially in the input vector space, j hat is to the left of I hat, right? And also in the output vector space, j hat, here is j hat, right? 1 comma 2 is, it is still to the left of I hat, right? So the orientation is not changed. So orientation is not changed. That's why the determinant is positive. It's 6, right? It's plus 6. So it's positive. Okay, because even after the transformation, the orientation of I hat and j hat remains the same with respect to each other or position, right? So this is an important thing, that whenever the position or orientation of the basis vector changes with respect to each other after the transformation, then the determinant is going to be negative. Okay, it will have some magnitude, but it is going to be negative for sure. Okay, now we will see some properties of determinant. Uh, Properties of determinant. Okay, so the first property is by the way, determinant is also represented using this triangle sign. So the determinant of A multiplied by B, the multiplication of two matrix A and B, the determinant of AB is same as determinant of A multiplied by determinant of B. Okay, so this is one property. Second property is determinant is also represented by the modulus sign. So determinant of A plus minus B, either A plus B or A minus B, is not equal to determinant of A plus minus determinant of B. So this property holds for multiplication. The determinant of AB is same as the determinant of A into determinant of B, but it doesn't hold for plus and minus. Okay. Determinant of A transpose is same as determinant of A. Okay. Fourth one is determinant of A inverse is same as 1 upon my determinant of A. So this is simple, I think. So determinant, so for example, 3 inverse is what? 1 by 3. So this is something like that. Okay. Fifth one is you have a scalar C times the matrix A. So determinant of C times the matrix A is C to the power n determinant of A, where A belong to n cross n. A is an n cross n matrix and C is some constant, some scalar value. Okay, so if A is an n cross n matrix, like say, let's say 3 cross 3 matrix, and you are multiplying that 3 cross 3 matrix with a constant, let's say 5, then the determinant of 5 multiplied by that matrix is same as 5 to the power 3, because A is a 3 cross 3 matrix and determinant of matrix A. Then we have this property. So if we have this matrix A1, A2, A3, B1, B2, B3, C1, C2, C3. Okay, and then we simply add some constant K, uh, K1, K2, K3. Then this is same as if we simply split it A1, A2, A3, B1, B2, B3, C1, C2, C3, then plus, then we will simply write K1, K2, K3, B1, B2, B3, C1, C2, C3. So these properties are important for exam point of view. Okay. Now there is one more property called the invariance property. So by the way, this is the sum property. This is the sum property. Now we have the invariance property. Invariance property, which goes something like this. If we have A1, A2, A3, these are matrices. So determinant of this matrix C1, C2, C3 is same as determinant of A1 plus some alpha constant alpha times B1 plus beta times C1, A2 plus alpha times B2 plus beta times C2, A3 plus alpha times B3 plus beta times C3, B1, B2, B3, C1, C2, C3. You can prove these properties, but like it is out of the scope, even for exam point of view, and it will just stretch the video. So I'm just writing down the property, but if you want to explain me these properties, then let me know in the comment. I will explain, but yeah, it's not needed as such. All right. Also, for example, we have this matrix A1, A2, A3, B1, B2, B3, C1, C2, C3. Okay. If we interchange any two rows or columns, then the sign of determinant will change. Okay. So if we interchange any two row or column, then the sign of determinant of A will be changed. Okay, so you can simply say, for example, this is A, and let us suppose this is B. B is nothing but the same matrix, but the two rows are swapped. The row 1 and row 2 are swapped. Okay, then in this case what I can say is the determinant of B is nothing but minus times determinant of A. This is the most important property from exam point of view, because where a lot of questions are asked from permutation matrix and determinant. So this is important property. We will solve some questions on that later on. Okay. So I think, yeah, one more is the determinant of a diagonal matrix or determinant of a upper triangular matrix is nothing but product of diagonal elements. So it's very easy to calculate the determinant. Also, one more thing, the determinant of an orthonormal matrix is plus minus 1. We will see what is an orthonormal matrix in later lectures, but yeah, I just mentioned this. So these are the 10 important properties of determinant. Okay, so now our next topic is adjoint. Just give me a minute. Uh, Adjoint. So how is adjoint calculated? So it's very simple, by the way. So for example, we have this matrix A, which is A11, A12, A13. This represents the position A21, A22, A23, A31, A32, A33. Okay. So we will first see what are minor. Okay, what are minors? Because minors and cofactors are used while calculating adjoint. So what is minor M11? So what you do is simply you remove the row and column at the location 11. So this is the location 11. So you simply remove this row, sorry, this column and this row. Okay, whatever is left, this thing, the determinant of that remaining sub matrix is minor M11. So the determinant of A22, A23, A32, A33 is M11. Similarly, you can calculate M12. How you will calculate? You will remove the first row and the second column. Whatever remaining sub matrix is there. The determinant of that is a M12. So it is you remove uh, uh, this and this, right? The first row and the second column, 1, 2. So you remove this, you will be left with 821, 823, 831, 833. Okay. So similarly, you will be calculating all the minors. So there will be total 9 minors. So the number of minors is the number of entries in the matrix. So there are 9 elements. So there will be 9 minors. Now you will calculate the cofactors. Calculate the cofactors. Okay. So the formula for cofactor is very simple. Cofactor of Aij is nothing but minus 1 to the power I plus j minor ij. Right. So basically, for example, what is the cofactor of A11? It is nothing but minus 1 to the power 1 plus 1 minor 1 1. Okay. Similarly, cofactor of A12 is nothing but minus 1 to the power 1 plus 2 minor 1 2. So this is nothing but 1 plus 1 is 2, minus 1 to the power 2 is 1. So this is just m11, and this is minus m12. So similarly, you will calculate all the cofactors, and number of cofactors is same as the number of entries in the matrix. Okay. So there will be 9 cofactors, 9 minus 9 cofactors. Now we will calculate the adjoint. So the adjoint is very simple. Uh, Adjoint of A. Adjoint of A is nothing but you just place all the cofactors A11, A12, A13, A21, A22, A23, A31, A32, A33, and at the end you take the transform. Uh, sorry, transpose. Okay. So this is adjoint. This is the adjoint of A. So I think it is clear. So actually adjoint it is not that important. It is not much asked in the exam. Because the GATE exam is more concept oriented, so you will see a lot of question from determinants, the properties of determinants, but not much questions from adjoint. But still, it's good to cover that topic. Also, adjoint is important from calculating inverse, because there are multiple ways of calculating inverse. One way to calculate inverse is A inverse is nothing but adjoint of A divided by determinant of A. So this is the most used way of calculating A inverse, adjoint of A divided by determinant of A. Okay. Apart from this, there are two other ways. One is you can calculate A inverse using the Cayley-Hamilton theorem. We will cover Cayley-Hamilton theorem in upcoming lectures. It's a miscellaneous topic. That is one way of calculating A inverse. So you have the characteristic equation, and then from that you apply Cayley-Hamilton theorem and calculate A inverse. Another way is using this using reduce row echelon form. We'll see what is reduce row echelon form. So in that you have the matrix A, and to the adjacent you write the matrix I. Then you apply the elementary row operations. Then such that this A becomes I. And once this A becomes I, whatever this I transform to, it is nothing but A inverse. So you just apply elementary row operation. You just try to make this A I. Once this A become I, at the same point this I become A inverse. So this is one way of calculating A inverse. So these two are the most used method of finding A inverse, adjoint of A and this. Okay. So this is how we calculate a inverse of a matrix. So in exam at max a 3 cross 3 inverse will be asked, not more than that, because GATE exam is not about finding inverses. They will ask you very concept oriented questions, right? But while solving some problem, you need to find A inverse. So at max you will be finding in A inverse of a 3 cross 3 matrix, not more than that. And sometimes you will be finding A inverse of a 2 cross 2 matrix. By the way, there is a trick to find A inverse of a 2 cross 2 matrix. Trick for 2 cross 2 inverse. So what is that trick? So basically, for example, if you have this matrix A, B, C, D, 2 cross 2 matrix, then its A inverse is nothing but you first take the what you will do, you simply swap these two elements A and D. So D came at the position of A and A came at the position of D. That's it. And you keep the position of B and C, but multiply them with -1. So that's it. Then at the end you divide by the determinant of A, and we know that the determinant of A in this case is very easy to calculate, which is nothing but 1 upon this is A into D minus BC. So AD minus BC. So this is very easy to calculate the inverse of a 2 cross 2 matrix. You don't even need calculation. You can simply do it in your mind and it will be easy. Okay. Apart from this, there is a property of A inverse also, that A inverse transpose of A inverse is same as if you take the transpose of the matrix and then take inverse. So this is also an important property from exam point of view, that transpose of A inverse is same as A transpose inverse. Okay. By the way, if any one of you don't know what is transpose, I will just for you just tell it, that for example, if you have this matrix A, B, C, D, then taking transpose is nothing but if you swap the rows with columns, right? So this is the columns, right? AC. So this will become row. The column AC will become row. The column BD will become the second row. So the columns become row, the row become column after transpose. Okay. So that this column AC become row, right? The column this column AC after taking transform became row, right? Similarly, this row AB after transpose become column. So this is what transpose is. Nothing big, but yeah, nothing. I mean, nothing interesting in that, but yeah. So I think that's all for today's lecture. What we have studied is, I just told you what is transpose, a trick to find 2 cross 2 inverse. The main thing I discuss in this lecture is what is adjoint, how we calculate adjoint, the properties of determinant, very important. I mean, just this is very important for exam point of view. It helps you solve a lot of problem. And the most important thing is what is determinant. I showed you visually that what is determinant, right? Okay, I think that's all for today's lecture. So if you think that these videos are helping you, then please like these videos, share my videos with your friends who are appearing for GATE or who are learning linear algebra or machine learning. Share my channel. It highly motivates me. Okay, see you then. Bye.